Hello, I'm Evan Wallace, president of Applied Fizzics. We've talked a lot about how CO2 comes out of solution with nucleation sites, agitation, and the like. In this video, we're going to look at how CO2 gets into solution. It's called forced carbonation. Let's get started. In this demonstration, I'm going to start with 500 milliliters of ice-cold water. This is water stirred with ice. It's probably not quite down to 32 yet, maybe 34 degrees according to my thermometer. I'm going to pour it in and put it on a kitchen scale. Now I'm going to put one of our Physio caps on this. It's a cap with a one-way valve that allows us to pressurize the bottle. And I'm going to tear out the scale so that it reads 0 grams. Now the next step is we're going to pressurize the bottle with a CO2 source that has a regulator that is calibrated to about 63 psi. As you can see here with the gauge, maybe 62. And now we're going to pressurize the bottle. I invert the bottle and put the handle of the CO2 source against the valve, pull the trigger, and you can see the plume of bubbles shooting into the liquid water. I put it on the kitchen scale, and we'll zoom in here, and it reads 5 grams. So we have put 5 grams of CO2, it's actually measurable, in the headspace of the bottle. Now I'm going to shake it vigorously to dissolve the CO2 in the liquid. The shaking helps because it increases the amount of surface area of the liquid in contact with the high pressure CO2. So what would have taken hours takes only seconds to dissolve. And we see, of course, that it still reads 5 grams because we haven't added or removed any CO2 from the bottle. Now I'm going to do this again. Once again, I pull the trigger, and you see a little less CO2 flows in this time because the water has already taken up a good amount of CO2, 5 grams or so, and we shake it to again speed the diffusion of CO2 into the liquid because of the increased surface area. And now we have 8 grams of CO2 inside the bottle. Some of it's in the headspace and some of it's in the liquid. We don't know how much yet. Let's keep going. We try it again. More CO2, but less this time than before. We shake it up, put it back on the kitchen scale, and now let's zoom in, and we're up to 10 grams. So we have 10 grams in the bottle. Again, some of it's in solution, some of it's in the headspace. We don't know how much is within each portion of the bottle yet. And let's try it one more time. Again, slower this time because the liquid is becoming saturated. It's coming to equilibrium. We shake it up one more time, put it on the scale, zoom in, and we got 1 more gram in. Let's try it one more time just to see if we're at equilibrium. And the key determinant of whether or not it's at equilibrium will be whether or not we can put any more CO2 in solution. And as you can see, very few bubbles went in this time, and we shake it and weigh it, and we're still at 11 grams. So that's a real good indication that we are in fact now at equilibrium since the weight on the scale hasn't changed. But I mentioned that we don't necessarily know yet how much of that CO2 is in solution and how much is in the headspace. So I'm going to let the pressurized CO2 in the headspace out by unscrewing the cap and then see how that changes the weight of the container on the scale. Well, now we've dropped to 7 grams. We were at 11. So that means that we have 7 grams of dissolved CO2 in solution, and there were 4 grams in the headspace that we released. And now we can check out our handiwork. Let's see what 7 grams of CO2 dissolved in 500 milliliters of cold water looks like. Well, it's a very fizzy carbonated water. Very vigorous carbonation at roughly 34 degrees, 62 pounds per square inch equilibrium pressure of CO2. And that's forced carbonation in a nutshell. In Field Notes 8, we'll look in more detail at that split between what's in the headspace and what's dissolved in the liquid. We saw we had 4 grams in the headspace and 7 in the liquid, which is about a 60-40 split roughly. Turns out to be typical for a lot of carbonated beverages. What's even more amazing is that the dissolved CO2 in the water is a little more than the weight of a quarter. So all of that fizz comes from an amount of CO2 that's about the weight of a quarter. I think that's pretty amazing. Thank you for watching, and tune in next week for more applied physics of your favorite beverages.